Hello everyone, welcome to our talk about field-aware calibration, a simple and empirically strong method for reliable probabilistic predictions. My name is Feiyang from the Institute of Computing Technology, Chinese Academy of Sciences. This is joint work with Tencent and Tsinghua University. So nowadays, large companies are using deep learning for decision making. To make reliable decisions, it is at the heart of machine learning models to provide accurate probabilistic predictions. So, to start with, let's consider a standard supervised learning problem with binary outcomes. Here I'm showing two examples. The first one is a binary classification problem, where we would like to classify whether an email is a spam or not. So given an input email, when we make a prediction, we will simply classify it into the positive class or the negative class. On the other hand, we see the second example, which is to forecast whether it will rain or not. So in this case, we not only need to make a classification, but we also need to give the confidence of the prediction. So in this case, we will have some probabilistic prediction say that it will rain tomorrow with a probability of 80%. And then there is another case, which is also very common in many real applications on the web. For example, in advertising or recommender system, we can decide which ad to push to the user or which item to recommend only after predicting the click-through rate of every candidate. So in this case, we care only about the probability of getting a positive outcome. Now let's consider that when can we say a prediction is reliable? So in this work, we connect the reliability to calibration. We say a prediction is well calibrated if the actual positive rate matches the prediction. For example, when we predict that it will rain tomorrow at 80%, the actual probability should also be 80%. So currently, considering that most of us are using deep learning models for our applications, let me ask you a question. Do you think that deep learning models are calibrated or not? So unfortunately, the answer is no. Here I'm showing a famous ICML paper, which showed that modern machine learning models, especially deep neural networks, can yield poorly calibrated predictions, which definitely hurts the reliability of the decision-making systems. Specifically, the model's confidence does not match the observed accuracy. For example, in this figure, we see that when the model's confidence is 80%, the actual accuracy can be lower than 50%. So, in light of these observations, we are motivated to develop some practical methods to deal with the issue of miscalibration. So, here is a summarization of our work. We consider two problems. The first one is, how do we measure the quality of probabilistic predictions? So we put forward a new type of evaluation matrix named field-level calibration error, which measures the biases of predictions in different subsets of the data. And the second question is, if we know that the predictions are miscalibrated by using some validation set, how can we fix them? So conventionally, the calibration methods such as plot scaling and isotonic regression are just univariate mappings. On the contrary, we propose a new type of calibration methods named field-aware calibration, which takes all the input fields into consideration. As an instantiation, we propose a simple but powerful method named neural calibration, which has shown to be effective in many real problems. So now let me briefly introduce the background. I'm going to first go through the notations and existing evaluation metrics for calibration. In this work, we consider the most basic binary classification setting, where we have samples in the form of pairs of x and y's. And we consider using deep learning models to make predictions. So the prediction we want is the probability of getting a positive outcome. To get this prediction, the model would first get a real valued output, namely the logit. And then by applying the sigmoid function, we can get the prediction p hat, which is between 0 and 1. Now let's see the common metrics to evaluate the predictions. So a straightforward way to measure miscalibration is to average the errors over all the instances in a holdout dataset. Here we name it as the instance level calibration error. For example, we can use negative log likelihood, also known as the log loss. Also, we can use the Breyer score, which is defined as the mean squared error between p hat and y over all the samples. Therefore, by minimizing such a instance-level calibration error, the overall prediction bias will be smaller. However, there is a drawback that they cannot measure the biases in different groups of instances. And later on, we will show an example to demonstrate that a model with a small log loss can still be miscalibrated. And next, in many previous studies, the calibration error is formulated by partitioning the predictions into bins and summing up the errors over the bins. We call it the probability level calibration error. Here we show a reliability diagram, which can be understood as a visualization of this metric. The intuition behind this metric is, for every subset of data where the predicted rate is p, the real positive rate should also be around p. But so it has a drawback that the subsets are split according to the prediction, which can be unstable in practice. For example, if we give very similar predictions to all the samples, the prob-ECE can be very small, which is undesirable. So in this work, we do not include prob-ECE as an evaluation metric. And finally, of course, we have some non-calibration metrics, which mostly cares about the classification accuracy or some rank-based measures such as the AUC score. These metrics are probably the most important ones in the industry, but they do not consider the miscalibration problem at all. So okay, that's all for the evaluation metrics, and now let's see some existing calibration methods. In general, we suppose that there is a holdout validation set where we can obtain a calibration function. So a calibration function is often a univariate mapping from the original model output to a calibrated one. So previous calibration methods include the parametric method, Plath-Scaling, which is basically to learn a logistic regression model between the prediction p hat and the labels y. Or we have non-parametric methods following the idea of binning, for example, histogram binning and acetonic regression, which are also commonly used in the industry. So to use these methods, the learning pipeline is simple. First, we can train a model on the training set, noted by model 1. Next, we can learn a calibration function using the validation set. And finally, we can use them to make predictions. So now let's come to our first contribution, a new type of evaluation matrix. So now, let's suppose that the input of the classification problem includes one special categorical field, z, which is some attribute the decision maker especially cares about. Given that z is a categorical attribute, we can partition the input space into a number of disjoint subspaces. For example, here we show a dataset with two input fields, the user ID and the item ID. So if we care about the biases on the items, we can firstly divide the dataset by row. So now each row represents the history data about a single item. And then for each item, we can compute the discrepancy between its average predictions and its average outcomes. So next, by calculating a weighted average over the absolute values of the discrepancies, we can get the item level expected calibration error. And similarly, if we care about the relative error instead of the absolute error, we can compute the field level relative calibration error. So now we get two new metrics, which is the field ECE and the field RCE. So the essential thing here is that we need to divide the dataset into subsets. And then we compute the discrepancy between predictions and the actual outcomes within each subset. And finally, we can get the average over all subsets. Now we are going to show some motivating examples. So here we have a public dataset for long default prediction. We want to predict the default rate given the user's attribute and long histories. Here the field Z for field level calibration error is which state the user lives in. We will compare the original Model 1 with the calibrated predictions given by Plath-Gowling and isotonic regression. By showing this dataset, we would like to demonstrate that how severe miscalibration can be. Now we show the results. First, we see that the calibration error of Model 1 is very large. The field level relative calibration error, the field RCE, is about 50%, which is obviously unacceptable. But fortunately, calibration helps a lot. By using Plath-Gowling or isotonic regression, log loss as well as the field RCE can be lowered. However, since the calibration mappings are monotonic, the AUC score does not change. So many of you might wonder that, since we've already got a validation set, why not just use it to fine-tune Model 1 so that we can have a better model? And maybe by doing so, the miscalibration error will just disappear. So certainly we can do that. We can do the fine-tuning, and we call the resulting model Model 2. So now let's see how it performs. Here is the results. Indeed, Model 2 gets a higher AUC score and a lower log loss comparing to Model 1, which is just great. But as for the field level calibration error, the field RCE of Model 2 is over 100%, which is just crazy. So what we can learn from this is that adding more training data does not necessarily result in a lower calibration error, even when the model gets a higher AUC score or a lower log loss. And similar things have also been found in other tasks. So in this famous click-through rate prediction dataset of Cretel, we found that Model 2 is better than previous calibration methods in both AUC and log loss, but it still suffers from a large field-level calibration error. So now we come up with a question. Can we simultaneously achieve both a high AUC and a low calibration error at the same time? And our answer is yes, it can be achieved by using the field-aware calibration. So the method we propose is called neural calibration, which is a field-aware calibration method. The overall structure is shown on the slides. It consists of two parts. The first part is a parametric univariate mapping function named isotonic line plus scaling, which transforms the original model output into a calibrated one. And the second part is an auxiliary neural network that takes all the features as input, which is to fully exploit the field-aware information in the development set. Now let's go into the details. Well, formally, the prediction is a sigmoid function of the sum of the two parts, with eta the function of the logit and g the function of the original input. Note that when using neural calibration, we do not need to specify the special field z. We just take all the features at input. Here the function g is implemented by the same base model, which can be a neural network. So in order to train the whole calibration model by gradient descent, we would like to use a parametric function as eta. So we propose a novel univariate mapping named isotonic line plus scaling. It has the name because it is isotonic, and it looks like a line plot. You can find a detailed formulation in the paper. So intuitively, isotonic line plus scaling combines the ideas of both binning and scaling. It is parametric, continuous, non-decreasing, and differentiable almost everywhere, which are some important properties. Finally, we conducted extensive experiments to verify the effectiveness of our method. Now let's have a look. So we tested over 5 datasets, where 4 of them are from Kaggle and 1 is from a real advertising system of Tencent. The data splitting is done without a shuffle. So the experiment pipeline goes like this. For each dataset, we firstly train a base model, namely the Model 1, on the training set. Next, on the one hand, we train the common calibration methods as well as our neural calibration on the development set, which is the validation set, based on the logics given by Model 1. And on the other hand, we make a copy of Model 1 and incrementally fine-tune it over the samples from the development set. So the model is called Model 2. And finally, we use a holdout test set to evaluate all the models. As for the evaluation matrix, we use log loss, the Breyer score, the AUC score, and our field ECE and field RCE. The full experiment results can be found in the paper, and here we only show 3 representative metrics in the slides, which are the log loss, the AUC score, and our field RCE. Now let's first come to see the low-end dataset, which is mentioned previously. We can see that neural calibration got a higher AUC than Model 2, but also had less calibration error than the other methods. And similar results have been observed in all 5 datasets. So let me just show them at once. So in all the datasets, the AUC of neural calibration is either comparable or higher than Model 2, and is much better than previous calibration methods. This is great because, after all, AUC is a very important metric in real applications. Then we see that neural calibration is consistently better than the other methods in log loss and field level calibration error, which shows that neural calibration is really an effective calibration method. And specifically, in our proposed metric, field RCE, neural calibration is an order of magnitude better than the base models, Model 1 and Model 2, on the first 2 datasets. So these results are evidence that neural calibration can indeed reduce the error and make the probabilistic predictions more reliable. We have also done a number of ablation studies, and we show that by using isotonic line plot scaling alone can already outperform plot scaling and isotonic regression, and the auxiliary neural network further improves upon it. And we also verified the effectiveness of using all the features to train neural calibration. And finally, we found that in the face of distributional shift, previous calibration methods tend to make bad predictions, but our method still works well. So the details can be found in our paper. Finally, to conclude, we have these 3 take-home messages. First, if we care about the reliability of probabilistic predictions, we should try to evaluate the model using the field-level calibration errors like field RCE and field ECE. This is because even when the model gets a nice AUC score or log loss, it can still suffer from large field-level calibration error. When the error is large, it means that the model is unfair to different groups of the data. And second, comparing to previous calibration methods that learn a univariate mapping, field-aware calibration that takes all features into account can be more helpful. And finally, neural calibration, as a simple instantiation of field-aware calibration, is effective in many real applications. So the key benefit is that it can simultaneously achieve a high AUC and low calibration errors. So okay, that's all for the talk. Thanks for listening.